So let's look at the motion of a charged particle in a magnetic field. What we're going to notice is that when a charged particle is moving in a magnetic field, and we apply the right-hand rule to it, we discover that in fact the force is a centripetal force. What do I mean by that? Again, we have V cross B. Now the magnetic field is going into the board right here. So if the velocity is here and the magnetic field points into the board, the force goes this way. That's going to cause the velocity to change a little bit. Instead of being all in the positive y direction, now it's going to be a little bit off to the left. Now with the new velocity, v cross b, it points again toward the center of this radius of curvature. So as the force is applied to this charge, it's going to force it in a curved path. The curve is going to be constant because the force is constant, and it will eventually come full circle. Now, what we remember from centripetal forces is that the magnitude of the force is equal to the mass times the velocity squared divided by the radius. So we're going to take that force and we're going to balance it with the force due to a magnetic field. Now here is our force due to a magnetic field. Q, V cross B has been changed to just VB. We're not using sign here because we're assuming that the velocity and the magnetic field are perpendicular to one another. So the sign, in this case of 90 degrees, is equal to 1. QVB becomes equal to mv squared over r. So if we want to solve for the radius of the curvature here, we can simply move r over here. We have v right here and v squared here, so this v is going to cancel out with one of the v's on the right. Move the radius over to the left, and the radius is equal to the mass times the velocity divided by the charge times the magnetic field. So really, this radius gets larger and larger as the mass of the particle becomes larger or the velocity becomes larger. In fact, we can say the radius is proportional to the momentum of the particle. The radius of the trajectory becomes smaller as either the charge becomes larger or the magnetic field strength becomes greater. So what happens if the velocity isn't quite perpendicular to the magnetic field? Now, in the original case, the magnetic field and velocity were perpendicular. And even with this force on here, the velocity for this case was always perpendicular to the magnetic field. It was in the xy plane, whereas the magnetic field was in the z direction. Okay? In this case, actually, the negative z direction. If we were to give the velocity a slight z component, instead of following a perfect circular trajectory, that z component would give it a helical trajectory. So again, looking at our particle moving in this magnetic field, now instead of doing just a circle, the radius of curvature is going to be the same. It's going to be related to the perpendicular component of the velocity. Now it's going to follow a helical path, and that speed along the helical path is the z component, or the component in the direction of the magnetic field. Again, if we sort of think about this, the force is always perpendicular to the magnetic field, so it doesn't speed up or slow down along this magnetic field. But again, because it had a component in that particular direction, whatever the velocity was in that direction before, it's going to remain. So it's really, again, just a circle with an additional movement in the same direction as the magnetic field. What's interesting is if we take our magnetic field and we create a gradient, this creates what's called a magnetic mirror. Now, again, if this particle has a velocity with some perpendicular component to the magnetic field, that is going to be related to the radius of the curvature. But the parallel component is going to have it moving along the magnetic field lines. If these field lines converge, what actually happens is the velocity is no longer purely parallel. and it will begin to slow down as the magnetic field lines converge, and will actually change direction. So we actually can create what's called a magnetic bottle using a magnetic field gradient. For instance, if we have this positive ion right here, or a proton trapped in a magnetic field, the magnetic field looks like this, we can force it along the magnetic field lines so it can never escape. At each side, we increase the strength of the magnetic field and essentially create what's called a magnetic mirror. This is a way we can actually trap plasma. If we think about plasma, plasma is very, very hot matter. And plasma cannot be stored using conventional means. Okay? You can put it in a jar, it's going to give up its thermal energy to the jar and drop below its ionization temperature. And likewise, the plasma itself is going to heat up the jar and possibly melt it. So again, a physical container is not really effective in keeping plasma. However, using a magnetic field, plasma is charged. We can trap that plasma and really confine it to some region. Again, here's another look at one of these magnetic bottles with mirrors at each end. The radiation belts around the Earth. These were discovered early on in the space exploration program. We named them after its discoverer, Van Allen, called the Van Allen radiation belt. And there's an inner belt and an outer belt. And if you remember that the radius of curvature is actually related to the charge in the magnetic field. I should say the radius of curvature gets larger as the mass gets larger. So typically the outer belt is populated by protons, whereas the inner belt would be populated by electrons. Now, the Earth's magnetic field is very, very important because it shields the Earth from direct exposure to solar wind. The particles in the solar wind cannot travel perpendicular to the magnetic field lines. So in fact, they will travel along the magnetic field lines in these helical trajectories. In some cases, they'll even get trapped by the field gradient of this field. And that creates these radiation belts where these charged particles reside. In the case where the solar wind disrupts the Earth's magnetic field, we can actually squeeze these regions and cause some of the particles from the radiation belts to go along the magnetic field lines in the North and South Pole, or some of the charged particles in the solar wind can make their ways down along the poles. This will result in some of the charged particles colliding with the upper atmosphere, the ionosphere, and producing these very beautiful auroras. Again, solar storms are typically magnetic clouds of plasma. They travel toward the Earth, they disrupt the Earth's magnetic field, squeeze any trapped particles in there, causing the magnetic field lines to change and opening up a window for charged particles to reach our atmosphere. Again, we're pretty much protected from most of the radiation from the sun. Most of it's going to be completely deflected by the Earth's magnetic field. Even in the case of a very intense solar storm, all that's going to do is compress the field lines and jar loose some of the charged particles, much less than what's contained in the solar wind, and they'll reach our ionosphere and produce a beautiful aurora. In some cases, however, rapidly changing our Earth's magnetic field can induce large currents in wires on the ground. This can actually lead to blackouts as we overload our power grid. It's also dangerous to satellites because satellites will orbit above our protective atmosphere and can experience more radiation and failures associated with that radiation. But again, typically we'll see the aurora take place in the north and the south parts of our globe, and that's when we have these charged particles which are essentially leaking down through these magnetic field lines. And again, the Earth's magnetic field is pretty good at acting like a magnetic mirror and keeping most of these charged particles from hitting the atmosphere. But as you can see in this ultraviolet photograph right here, during intense auroral activity, some of these particles do make it down there.